Hello! There is a fascinating motto in the PL community, and this motto is that freedom is slavery. In this presentation, I will try to explain it more. Hopefully, you can learn about it and maybe even disseminate it. I think it's a very true motto. It is highly connected with the concept of offensive programming. Your code should monitor its execution and throw error as soon as anything goes out of the predicted path. Hopefully, you should fail with a good error message explaining what's going on. Offensive programming is fundamental when working on large projects. Consider the following three scenarios. In scenario number one, we have one programmer for a few days with no planned maintenance. They are just coding at something. This is just something that they want to code for themselves, like a little tool that they need for something specific to automate their workflow, some kind of scripts or something. Usually the user is the programmer themselves. In those situations, there is usually no real focus on security. As a second example, consider like a small team of programmers working in a company, and they will work on a project for a few months. Here we usually have an actual maintenance plan, and usually the customer is either a wealthy individual or a small company that wants some specific automation designed for them. Here, security starts to be relevant. As a third example, consider something big, made by many different individuals that doesn't really know each other so much, a community effort that will go on for many years. In this context, maintaining is developing. For example, is Firefox actively maintained or actively developed? Is GIMP actively maintained or actively developed? It's one and the same, right? In those cases, usually there is no a clear customer, but a large user base. And here, security really becomes so important, and at the same time, it becomes so much harder than in the second scenario, because we don't have a good control on who are our customer, and we have way more programmers and they keep coming and going into the project. That is, if you program at a small scale, programming is mostly just a tool to express behavior. And of course, when we start coding, we just teach you how to code in the small scale. And so you may end up with the misunderstanding that all coding is just an exercise in expressing behavior. However, when we move to a larger scale, you see that programming becomes more and more as a way to constrain behavior, to restrict behavior, so that we can keep control on what's happening in this piece of software that is so big that we can't possibly wrap our head around it. Moreover, we change over time. So even if we are the only person working on a big piece of software, when we come back 2 months after, look into the software that we wrote in the past, it will be no different than looking to software wrote by an entirely different person. Now, one solution is to properly document your code so that whenever someone needs to understand what's going on, they will read the documentation and have a perfect idea what was your master plan, and they will be able to follow it and go forward with it. Too bad no one actually read the documentation. Offensive programming is like a form of active documentation. If your code can check how it is executed and throw an error when it is executed out of this expected master plan, well, people that use it will have to care, will be notified of what's going on, and they will basically receive a little snippet of relevant documentation in the error message. Or maybe a pointer to a specific page to look in the documentation if that's what you choose. And in that case, they will read it, because if they perceive that their work is stuck no matter what until they read that 20 lines, they will actually go and read those 20 lines of text. In some sense, you can think about programming as a competitive effort, but also as a battle. So consider a multiplayer shooter or similar game. Today, they just released a new update, yet another kind of weapon. From an attack mindset, you could say, oh, cool, yeah, now I can do yet another thing. More freedom, more expressive power. Still, I can only keep up to 4 weapons in my inventory. But on the defense point of view, the situation is very different. Oh no! There is yet another way the enemy can kill me now. I have to keep in account this other way so that I can protect myself from all the possible kinds of attacks. Consider now a programming language. There is a new update, yet another kind of statement, expression, feature, language primitive. For example, an extra reflection capability. If you are in the initial development of a project, you look at it and say, oh, cool, a new thing that I can do. More freedom, more expressive power. Still, my brain is finite, so I can only keep in my head a finite set of features in every moment of time. Then, look at it from the maintenance or usability perspective. Oh no! Now my user and my coworker can interact with my code in yet another way. And now I have to be sure that all the interactions coming also from this other way are safe, so that my code will not break down even when it's used in an adversarial environment that contains also those new features in. How can I make sure that my code is correct in all those scenarios? Continuing on the video game metaphors, we can imagine 2 kinds of programming environment. We can have a cooperative environment. This kind of programming environment is what is commonly associated with Python or Ruby. A user of your code can always break or dismantle absolutely everything if they want. The only documentation giving full information of what will happen if they start playing, editing the value of variables on the stack trace or monkey patching methods is the source code. The only documentation that gives you this complete information will be the source code. This gives user full freedom and gives the library writer full slavery. They basically cannot fully guarantee anything. That may be not too bad for small projects where we can rely on conventions and cooperations and hope for the best. Minecraft is great for cooperative playing, where many builders can come together and build amazing things. In Minecraft, it's reasonably easy to not step on each other's feet while we are building. On the other side, in programming, it's so much harder. For example, if my wall is not very stable, your house will not collapse. In programming, this is not really the case. A collapse in my part of the code may break your system too. Still, cooperative Minecraft servers usually have a reasonably small number of players. The more the players, the more the risk of a griefer getting in. This is the same for coding. If your project is big enough, or if breaking your project is worth enough money, you may not be able to get enough trusted programmers to work on it. Also, do you know about supply chain attacks, where the hacker managed to inject adversarial code in one of your dependencies, so that when you update your dependency to the new version, you are also importing arbitrarily adversarial code into your project. You're going to have a lot of different programmers working in your setting, and maybe some of them you can trust and some of them you cannot trust. And if you're using third-party dependencies, in some sense, all the programmers of those third-party dependencies will need to be somehow trusted. And there are so many things that can go wrong. Not only one of your programmers could actually be the hacker, but one of your programmers may lose his access credential in some way or get his system sizely compromised, and now a hacker can commit on behalf of that programmer. And if he is just so sizely distracted, he may not recognize that this is happening. And so I'm introducing you PvP programming. What? I assume you're now opening your eyes very wide. What will a PvP programming environment look like? I mean, PvP Minecraft servers are basically giant wastelands. How can PvP programming end up any better? How could we not just end up making big barriers and everyone just recoding everything themselves because they can't trust anyone else's code, and anyway anything's slowly falling apart and no way to build something big and functional? No, there is a solution. But to understand this solution, we first need to approach the theme model delusion. You see, there is a big lie in programming. The lie is that ultimately everything is broken. Thus, the best we can do is to just be sensible, practical, and to try to cooperate. Yeah, there are all those people writing fancy type systems and proofs, and those helps, but they are just basically tools that we can use, that they can support us writing good code, but ultimately everything is broken. There will be a way to circumvent whichever protection they try to give us, and so we just need to be practical and try to cooperate and accept that if someone wants to be a jerk, they will actually be able to hurt us. In the old C, shell, system programming, low-level operating system programming, this is correct. On this mindset, programming languages are just a nice way, a nice tool to generate arbitrary assembly. And so, since you can generate and run arbitrary assembly, eventually everything is broken. In the end, everything can happen. In the end, absolutely anything can happen. Thankfully, we are slowly moving away from it. In Java and C# and Haskell, a bunch of things are actually guaranteed by the language. This is why Java has security bug fixes. Because they have a security model, some properties that the language actually consider under their responsibility, some kind of properties that they actually promise to be preserved. Yeah, in a C, C++ compiler, there is no such thing as a security fix, because there is nothing to fix. It's not because C is intrinsically more secure, but because C is not promising any security. All the security have to be provided by the programmer, and nothing is the responsibility of the language. In Java, C# and Haskell, it's actually possible to write good offensive code that's actually guaranteed to work modularly. No matter how adversarial the user context is, your code will still be able to preserve internal constraints and to monitor its behavior against abuse. Up to a point. However, this is very unpractical in the general case. Those internal constraints that you can enforce offer no protection from actions like input, output, and so on, and usually that's exactly where we would like our security to focus. And anyway, this is false if you load broken C code. In that way, you can send the process in undefined behavior and everything can happen again. That is, having in those contexts, if arbitrary adversarial code ends in the system, then we move to this real PvP scenario, and we are indeed back into the desolate wasteland. If you are coding in C or C++, you are immediately into the desolate wasteland, while if you are coding in Java, there is a little bit of resistance. The language is trying to keep some properties, but if the user somehow loads broken C code, all the bets are off. And even if they don't, any adversarial piece of code will be able to do new file and open a file and wreak havoc on your hard drive. Indeed, in many operating systems, just being able to write on an arbitrary file allows you to break absolutely every guarantees. On many Linux systems, there is a special virtual file that represent your running virtual memory. And so if you can write on that file, you can send your own process in undefined behavior. To this aim, I'm designing a new programming language called 42. 42 goes one step further and actually prevent all of the problems that we have discussed before. In 42, even if there is adversarial code running in your security critical 42 process, you can still build a secure fort, ensure arbitrary representation invariance of your objects. From those, you can build a strong and flexible security system where valid objects are guaranteed to only do valid actions. And you can make sure that only those objects are able to do those actions. And so, if there is arbitrary adversarial code, they will have to go through your security mechanisms in order to be able to have any impact at all on the system. To have any hope to get modular correctness or security, the code must be able to make sound assumptions on its internal constraint. That is, you want to be sure that you can write a module M, and that if this module M is placed in any context C, the internal invariance of M will never be violated. Again, in Java, C or Haskell this is hard but possible. In C, C++ or Python it's simply hopeless. Because, for example, in Python, user code can always disassemble and tweak any other code, and in C, C++, user code can always send the whole system into undefined behavior. And after that, the code of your module can do absolutely anything. Languages that are trying to allow for modular consistency, they have to go through some kind of trade-offs. They could be easier or harder to use. They could offer different kind of certainties of those behavioral constraints. And those behavioral constraints can be simpler or harder to express, and they can have more or less expressive power. So in 42, I try to be near as easy to use as Java. The behavioral constraints of 42 gives you security full certainty. This means that you can be certain that bad actions never happen, but you cannot be certain that good actions will eventually happen. The system could simply throw an exception or go in loop and never progress. So, in particular, I'm not defending you from any kind of denial of service attack, but you can address basically any other kind of security vulnerability in 42. Those behavioral constraints in 42 are expressive and intuitive in the sense that the system is metacircular and you can use the 42 language itself to express those properties. In other settings, you may need different layers and different languages, and maybe you may have to express your security properties in some logical language that will become yet another thing that you have to learn and understand. That is, I'm designing a new language with the goal of allowing radical security even in the context of PvP programming. I'm not encouraging anyone to purposely be adversarial while they are coding, but if a language cannot ensure safety properties in a PvP programming environment, then this language is not actually providing any guarantees. Just a tool that helps you to write good code. What I'm trying to create is a system that actually prevents problems. That is, we are trying to make a language where it is impossible to do certain kinds of error. No matter how you try, certain kind of properties cannot be violated. And we can obtain this by classify and mathematically model various kind of errors. And then the language semantic will prevent those errors. And of course, there is a cost. The language is now harder to use even in the non-PvP environment. And so this goes against, I would say, a common wisdom of trying to design a language to be as easy as possible to use to do simple tasks. I think this is a misguided objective because, again, freedom is slavery. The easier it is to do simple tasks, the harder it is to actually code in order to prevent behavior. Now, I will make an example showing you some Java code on how we can try to preserve some internal invariant in a good offensive programming style. That is, we want to monitor how our code is used and throw errors if something goes wrong. So we can have a simple class person with a string name, and we can have an invariant, the name is never empty. If the user tries to get a person with an empty name, they must fail with an error. Intuitively, we could just write this, class person, string name, and a constructor person that take the value for the field and initialize the field. But then, of course, the user will be able to do person invalid equal new person of an empty string. And we want to prevent this. We want to make so that this behavior is not accepted. We want to restrict this behavior. So we could just do this. Make in the constructor a check that if the name is empty, we throw our error. Sorted, right? That was quite easy. Now when the user tries to create the new person of empty string, they will just receive an error. Nah, it's easy to break. Just update the field after the object has been created. And now you have a broken person. That is, our program is wrong, but is not failing. So it's not offensive enough. Okay, so maybe all those gurus of object orientation that tell me that private fields are so important, we're actually onto something. So I will declare the field private, and I will make a getter and a setter. And I will check both in the setter and in the constructor that the string is not empty. Will this work now? Not if you write it like this. You can just use a try-catch. You try-catch your exception, and now you are able to access a broken person. Yeah, but come on, you should not try catch an error. This is clearly only designed for very special circumstances and like special kind of testing frameworks and something like that. But the language let me do it. I don't have to be cooperative. Any way at all that let me break your code is a good way to break it. Finally, if we swap the two lines and we first check if the input is valid before updating it, we now get something that solves also this problem. However, there are still a bunch of open problems. You could use reflection to update the private field. Well, great, in Java you can put a security manager to prevent that. But this security manager is sort of global, so we will need to say that our modules somehow have access to this global capacity of putting up a good security manager. Maybe you can just say that with an opportune security manager, Java is actually allowing offensive programming. Still, if the adversarial code is loading broken C code, it will be able to edit the bytecode of my just loaded person class, and guess what? Now they can do everything. Let's consider another example. Now our person have a list of allergies, and the invariant is that there are no more than 10 allergies. And here, taking, a lecture from everything that we have seen before, we can have a private list of string allergies. We can have a public list of string allergy getter, just return the allergies. And then we have an allergies setter that takes a list of allergies, and if the size is more than 10, throws an error. Otherwise, is doing allergies equal list.copy of my list of allergies. And the constructor just delegate the behavior to the field updater. Is this code correct? Or is there some way to break it? Yeah, assuming a good security manager and assuming that we are not loading broken C code, is this correct? Well, it depends. It's correct if list.copyOf behaves correctly. In the current Java standard library, list.copyOf creates a copy of the list in input, and this copy is going to be shallow immutable. That is, this copied object is going to throw a dynamic error if we try to do add or add all or other kind of operations like sorting, but it will not prevent the objects inside to be mutated in any way. Luckily for us, this is a list of strings, and strings are deeply immutable in Java. So in this particular case, list.copyOf is indeed creating a deeply immutable object out of this input. And so we can save it in our field, and we can even directly return it because the user code will not be able to use the returned list to edit our internal private state in any way. However, what if tomorrow there is a supply chain attack on the Java standard library, and list.copyOf now returns a normal mutable list of elements? Now our code will be broken because of a change in code that we do not control. Moreover, in Java or C# or Haskell, the more the invariant is complex, the harder it gets to write good code around it. In 42, this is so much more direct, and this is like the only piece of 42 code that I'm showing in this presentation. We have our person equal data with a string name and a string.list allergies, and we have a method invariant that starts with the annotation cache now. So cache now class method void invariant that take a string name that represents the value of the field name, a string list allergies that represents the value of the field allergies, and then we check with an assert that in 42 we represent with x. We have two conditions in our assert. We check that the name is not empty and that the allergy size is less than 10. And this is it. The data decorator will cooperate with cache.now to make sure that in no way anyone ever will be able to observe a broken person object. No matter how s.list is tweaked, no matter how string is tweaked, no matter how other piece of code could cooperate with all the C libraries, no matter what kind of reflection tricks we are going to try, there is nothing in the language that will allow the user code to break this module invariant. Now, those days I'm trying everything I can to popularize 42 and especially the ideas behind 42. So please go to see the 42 tutorial in video format at the Intro to 42 playlist, or go to the 42 website, 42.is, or directly to the YouTube channel with my name, Marco Servetto. So see you there if you want to continue this journey with me and dive in the philosophy and madness of PvP programming.